In today's show, we hear about a delicious-sounding subject that calls itself molecular gastronomy. Is there such a science? Well, as if to answer that, we meet a professor of molecular gastronomy who's worked with the top TV chefs. He'll tell us about his kind of science experiment, and you'll pick up a useful tip for cookery success.
You're listening to The Science Show on Cambridge 105.
In this section called Scientists at Work, we talk to people who, for some reason or another, find themselves working, researching or thinking about science in Cambridge, England. Well, we start today with a conversation I had with Peter Barham, a professor of molecular gastronomy. He was in town to give a talk about the science of taste and flavour, although he also holds another professor title in polymer physics, which is a bit more ordinary, I think, at the University of Bristol, in fact. He's also the editor of a journal called Flavour, which covers the science of molecular gastronomy.
Yes, and I just have to give a shout out here because that's the same name as Alan, Matt and Ruth's food show on Cambridge 105.
Incredible. That's on every Saturday morning. But how did they think of the same name?
Unsurprisingly, perhaps, Peter Barham has worked with a number of restaurant chefs, including Heston Blumenthal. You might know him of the celebrated Fat Duck restaurant in Berkshire. If you've ever heard Heston talking about cooking food, you'll have noted how he often debunks the myths of cookery.
Yep, I can recall one of Heston's challenges when he was talking about meat recipes. And not just one recipe, but nearly all of them say that you should brown the surface of the meat to seal the juices in. According to Heston's experiments, that doesn't do that. Anyway, I caught up with Peter Barham as he was just about to give a talk at Churchill College. So, adding to the atmosphere, as you'll hear, you'll catch the audience arriving as I grab him for this 10-minute chat. So, Peter, tell us what you do.
Well, I have 3 chairs in 3 universities, which is a great trick. So at Bristol University, which I've been based at for the last 40-odd years, I'm Professor of Physics, where I'm largely responsible for teaching, but I also do research in polymer physics, which is where I started out life. I also have developed 2 other careers, one in penguin biology and conservation, where I have a chair in Cape Town, and another one, which is what we're talking about tonight, in food and food science, molecular gastronomy, and I have a chair in Copenhagen, where I play up with that game.
OK. Defend the words molecular gastronomy.
They're completely indefensible. They shouldn't exist. They came about purely by accident. The first meeting with the organisation was held back in the mid-80s, I think, and it was organised by Nicholas Curti, who was a physicist at Oxford, and Elizabeth Thomas, to get a scientific meeting on the science of food, and good food at that. It had a fancy name, and the meeting was called an International Workshop on Physical and Molecular Aspects of Gastronomy, which is a horrendous mouthful. So when we had the second one, we just simply called it an International Workshop on Molecular Gastronomy. That's where the term comes from. It's utterly meaningless and, as you say, completely indefensible. It has been adopted so much now that I can't escape it, and I actually hold a chair in molecular gastronomy. So I don't know what it means, but that's what I have, a chair.
So it must be proper.
Well, yes, but it doesn't really mean that. It's really the science of deliciousness, if you like. That's a good definition.
Oh, that's nice. Tell me about deliciousness, then.
I mean, the sort of questions that fascinate me and why I'm interested is, what makes food delicious? Why can something be delicious? But more importantly, why can a food be delicious to one person and hateful and revolting to the person sitting next to them at the same time? And yes, that's absolutely true. Why is it I can prepare the same food in 2 different environments? One environment it's really delicious, another environment it's pretty awful. All these things happen all the time to us. So understanding what it is that makes food really great is a really difficult science. It involves every part of science. It involves starting with where the food comes from, how it's grown, how it's transported, how it's processed. Processing doesn't necessarily mean a big factory. It can be in a kitchen. A kitchen is nothing other than a chemistry lab, really. And then what happens to you while you're eating it? What happens to you after you've eaten it? Because all that affects your appreciation of it. And then what your memories of similar foods are previously. It turns out that when we really start to delve deeply, the things that affect our appreciation, our perception of flavour and deliciousness most are not the food and its taste. They're actually to do with the environment and psychology and how it's presented. So if I give you a food and tell you a wonderful story about it, the psychology of you understanding that story will actually give you a different impression of the food than without the story.
Okay.
So, for example, in restaurants, we have done experiments in restaurants. So if you go to a restaurant and the waiter gives you a story of the food, explains to you how it's been lovingly crafted by the chef, in one example. Another example explains to the bare science, another example says nothing. The people's perceptions of the food are different in each case. And depending upon the person, the explanation can actually be different. So the wonderful story of the loving chef's care and attention to detail will impress some people, whereas the detail of exactly how it was prepared and the temperature prepared at, and that give other people an impression. So you have to know not just the story you're going to tell, but who you're telling it to and what their experiences and ideas are. It's a very complex subject.
Okay, you've led me to my next question, which was to ask whether you actually do experiments.
I mean, I'm doing experiments on food all the time, sometimes accidentally. I'm actually in the process of writing a paper on satiety, how people determine how much they want to eat or drink, on the complexity of food. And I did this by chance, because for a different reason. I was actually looking at trying to figure out with some friends, just as a ad hoc experiment, whether they actually enjoyed the same food, having eaten the same food twice. So I prepared a menu, and then I asked the same people to come back about 3 weeks later and eat the same menu. What I did change was the wine I served. And the reason for that was the first time they came, I gave them a rather expensive wine. And the second time I hadn't got a bit left, so I gave them a rather cheaper wine. This is me being tight-fisted perhaps, but it turned out the one difference between the two meals was not their appreciation of the meal or the wine, but the quantity of wine they drank. They drank far less of the high-quality wine than the cheaper wine, without knowing what it was, because it was in decanters both times. So what that tells us is something about how complexity of a food can actually relate to how much you want to eat before you're satisfied. Another example of that is if I offer you as much of a chocolate as you want to eat, most people will eat as much as they can of a fairly bland, ordinary chocolate. Something like a milk chocolate, it's very sweet, for example, eat several bars. But if I offer you a very expensive, highly complex, with multiple layers to its aroma and its tastes, dark chocolate, you'll actually eat less of it before you'll say, that was great. So you will actually eat fewer calories, fewer sugars, fewer fats, if you're eating something which is more complex in that context. Now, on the other hand, there's another side to that. You can't use this directly to say it's a health benefit, because you've got to be really careful. The complex food is completely satisfying in a small quantity, and that means it has to be an enormous quality, not just any old quality. And that is the other problem. What is high quality for a person varies by person. And in fact, your perception of quality changes through your life. As you eat or experience in general more complex things, be it food or music or painting, anything, as you move up the complexity scale, so your liking, your preference also moves to the more complex. So as we experience more complex things, we tend to want more complex things. So we tend to move up that scale of complexity for what's just right for us at any one time. And if you push someone a bit beyond that, then they take a bit less of it. So if you think of a music analogy, someone new to it probably would take loads of Beethoven and not much Stockhausen. But later in life, they may take plenty of Stockhausen and less Beethoven.
I was looking at your book, and there was a section on food and temperatures of cooking or
and
ways of cooking.
There's a whole range of things that we've done over the past 10 or 12 years, well, no, 20 years probably,
Wow.
where we've been looking at the science of what happens to food in the kitchen and the difference between precision and experience. A simple story which relates to this. I was about 20 years ago in a restaurant kitchen with a one-star, Michelin-star restaurant.
Yes.
Quite a decent kitchen. I knew the chef very well. And I was talking to a pastry chef who was in the process of making some chocolate. And he was tempering chocolate, which is a fairly straightforward process of crystallization and nucleation, which to any physicist who knows anything about crystallization and nucleation is utterly trivial to control.
Yes.
All it is temperature. It's all you can control, nothing else. So he'd done this tempering, and he was doing it by the way that if you read a traditional pastry chef's book or chocolatier book, is to do with texture and glaze and stiffness, and terribly complex. And it's a really difficult process. But I'd never imagined for a minute it could be regarded as difficult, but he was doing this. And what happened was he'd been making a large batch of chocolate, and it went wrong. And he threw a tantrum, threw his spoon across the kitchen, said several words that probably shouldn't be repeated like company, and then calmed down a bit. I just said to him, what's the problem? He just said, well, I've messed up my tempering. And I said, well, why? He said, it's difficult, it's complex. No, it's not, it's easy. He looked at me like I was mad because I'm just some bod. I mean, I was a friend of the main chef. He knew I was a scientist and had some fancy handle, but that didn't mean I knew anything about chocolate to him. So I said, well, here we are, just drop another batch. He said, well, I've only got 5 minutes. I had to make the chocolate. Well, that's okay, 5 minutes is plenty of time. I said, no, it isn't, it's okay. Fine. I got my thermometer out, tempered his chocolate for him in about 2 or 3 minutes. He literally sat there open-mouthed. He could not believe this could be done. And then he bought a thermometer. So he actually learned. Explaining to him why it worked with temperature took me several weeks because he just didn't understand what was going on. He knew what happened, but didn't know why it happened.
Chocolate is reversible change.
Yes, well, chocolate is a really good one. I mean, chocolate is an example where it's straightforward, very, very simple physical process of crystallisation, and anyone can make it work.
If somebody on a food programme was listening to this, is there any one science fact you could give them that might change the way they cook?
I think the simplest thing I would say, science fact, is measure the temperature of your oven. Oh. Learn how your oven works. Some years ago, for the fun of it, I asked all my colleagues in the physics department at Bristol to take a thermometer home and measure the temperature of their oven when it was set at a particular temperature. Let's say it was 160 degrees, doesn't matter, it's irrelevant. And then we plotted those temperatures on a graph, and we had a beautiful bell-shaped curve, as you would expect, with the mean 10 degrees different from the actual target temperature. So overall, they were 10 degrees higher than the temperature. So if you do that, that will explain to you why your recipes don't work as they're supposed to, because they're set not the absolute temperature, the temperature of the person who wrote the recipe's oven. It's even worse than... So, I mean,
yes,
simple thing... So it's wrong. But if you do that, if you then know what temperature in your oven is and you go and cook for friends, or you borrow someone's recipe, all you've got to do is find the temperature their oven is, and then you can do the cooking. For baking, it's the only simple rule that you can follow, and all it costs you is a thermometer.
That's true. Although the parallax error on the knobs.
Yes, of course. That's what it is. I actually have got ovens which have got digital on them, and they are set correctly now, having had a discussion with the manufacturer about it.
Okay, we're coming up to your talk now. The room's filling up. Distill a little fact that from your talk.
I think the thing that I'm hoping to get across to people more than anything else is that they will learn that they don't understand how they taste, and they'll learn a little bit about what it is, where the flavour comes from and how it's constructed in their brains, and hopefully they'll go away with an open mind and do some experiments at home.
Excellent. Thank you, Peter.
Okay.
That was Peter Barham from the University of Bristol. Peter was giving a talk in Cambridge for the Cambridge Society for the Application of Research. So thanks to them for letting us in. You can find more talks given by the Society at the CSAR website, and we'll post that onto our podcast page. Incidentally, Professor Barham has a book entitled The Science of Cooking. His idea is that a kitchen is like a science laboratory, and that cookery is itself an experimental science. And I had a flick through the book, Roger, on Amazon, where Peter explains, for example, what happens when meat is cooked and why some recipes work and others just fail.
Okay. Well, this has always reminded me of a story from when I was teaching chemistry to a class of 15-year-olds. Now, the idea in my lesson was that chemical reactions could be made to go faster or slower, depending on what you did to them. And increasing the temperature of the chemicals by only 10 degrees means that the reaction rate doubled. So I looked for an example to explain that, and I said, well, if you're cooking something in the oven and you increase the temperature dial by as little as 10 degrees, the cooking ought to happen twice as fast. So one curious lad put up his hand and said, so what's 10 degrees in gas marks, sir?
Wah, wah. All right, well,
that's pretty much all for today's show. Scientists at Work is made by the Science Show team on Community Radio Cambridge 105. You can also find past episodes on the website www.cambridge105.fm. You can also subscribe to future podcasts with the iTunes Store. You can get in touch with us on the email science@cambridge105.fm or on Twitter @105science. Till next time, it's bye from the Science Show team of Roger Frost and Chris Crease.
You're listening to The Science Show on Cambridge 105.